presenting our presentation, which is called the optibox. I'm Amanda.
I'm Jason. I'm Ryan.
Okay, just a brief outline of what we're going to cover. We'll go over some background information, our goals for our project, cover the construction and testing of the device, and then look at the results. Okay, so first, the thing that everybody needs to know is what is a spectrometer. All it is a tool that uses the properties of light to produce various information about a given sample. It always has the following basic components. Some form of a light source, thank you. Some form of a light source, mirror or mirrors, a diffraction grating, which splits the light into its color components, a detector, and then some form of an analysis tool. We also need to understand what a polarizer is. To understand this, incoming light always has multiple states of polarization, and a polarizer, what it does is only allows one state of polarization to pass through. And our device utilizes two of these so that we can control the type of light coming in and the amount.
Okay, the motivation for why we're building a cell phone-based spectrometer. Spectrometers nowadays are pretty expensive, usually ranging between $1,000 and $10,000. They're bulky, take a lot of space in the lab. Usually they're 1.5 feet by 1.5 feet. They're not very portable. Usually you have to connect them to some kind of external power source. They're usually delicate, so you can't really move it without messing some of the components up. And usually if you're doing some kind of testing in the field, your sample will start to degrade by the time you get it back to the spectrometer. So the goal, what we're trying to do is we're trying to make a low-cost spectrometer that can be used out in the field, and it's cell phone-based. And basically, we learned the real-life example of this was the business students back in the first quarter. We learned about the finances and the marketing plan about it as well.
Okay, so the initial concept of our design was use programs and SolidWorks, as you all know, to sort of assemble all of our components together. Here we have our light source, which is the flashlight, or in our case, the light box. It passes through a case plate, which has wave plates and polarizers superimposed on top of one another. It passes through the case plate and hits a mirror, which our sample is mounted on, and reflects off through another set of wave plates and polarizer. Except here, the polarizer is adjustable. Afterwards, it hits the diffraction grating, and it ends up splitting that white beam of light into its varying color components. And then afterwards, we take a picture of that resulting spectrum. So here are some of the SolidWorks models that we designed. Here you can see our diffraction grating holder, which has two long rods protruding from the ends. So that way, if we were to build a box around it, it would be able to contain the diffraction grating without it being adjusted. We also have our flashlight tube right here, which would contain our flashlight and also an iris, so that way we can kind of focus the beam of light. This component will also be attached to a lens piece, so that way we can adjust it and allow the beam of light to focus and get us the best kind of spectrum. We also have male and female gear rotators, and this would allow the rotating polarizer to rotate. And what we were going to initially have was dowel rods, or kind of dowel rod, with teeth protruding from the end of it, which would connect here on the gear. And this way we would allow rotation to occur by sliding it back and forth. And we were going to allow 90-degree rotation both clockwise and counterclockwise, so we can achieve all states of polarization. We also have a thin case plate right here, and we decided to manufacture this ourselves, so that way we don't have to go through Dora Labs and end up spending some of the money in our budget. So this way we not only save money, but we also save the cost of the device itself.
Okay, so this is the construction of the pieces he just explained. On the left is the rotatable polarizer, and you can see the teeth that Shaggy was talking about, and this is where the rods would go that would allow it to move. In the middle is the diffraction grating holder, and right now it's being secured with optical pieces, but once we construct the outer casing of the box, it will be screwed in. And on the right is the sample holder, which is just a small piece of PMMA, which has been etched out to hold a cuvette, and it has been threaded on the bottom so it can be secured through another optical piece. These are the external components of our device. The top picture is kind of everything, so you can see this is our light source with goosenecks coming out so you can stick the light in into the flashlight tube. The bottom left is this flashlight tube, which contains an iris and a lens to focus the light. And then, there we go. This is a first set of wave beta polarizers, and this one's stationary. On the right is just a close-up view of the light source so you guys can see it, and it will eventually be replaced with a portable flashlight.
So then what we did is we compiled all those pieces onto an optical breadboard to ensure that they were stable and they weren't moved. And then it follows the same path of light as we discussed in the initial concept. So it kind of goes to their polarizer pieces. Diffraction gradient and spectrums posted on the back right. So then for testing, initially we were planning on using the iPhone, but the iPhone is very limited in its technical settings. You can't change its ISO settings, its nighttime settings. So we switched to the Galaxy Note. And for samples, we used liquid food coloring because there's no absorbances. And then for our biological sample, we used hemoglobin.
So here's the general spectrum we achieved without any kind of hindrance from our samples. And as you can see, we get the full range. We get blue, green, yellow, orange, red, and some violet over here. And what happens is once we stick the samples within the beam of light, you would end up seeing a sort of decrease in intensity between the colors depending on what the absorbance is. And by dividing this spectrum with the sample spectrum that we achieved as a result, actually it's the other way around, we end up with a sort of ratio of what photons we're able to pass through our sample. And in the end, that will give us our absorbance. So we decided to use a MATLAB algorithm that we've developed in order to, well, achieve our absorbance spectrum as a result. We start off by reading in our sample image, depicted here, and a blank sample as well for comparison. Afterwards, we rotate the spectrum so it's perfectly horizontal, which will allow our code to analyze it more efficiently. Afterwards, we cut out the noise in the image so we can get a much better absorbance spectrum. Then afterwards, we shift the images so both spectrums overlap ideally. Now these are actually blue, green, and red peaks, sort of superimpose one another and combine. And as you can see, the peaks do match up pretty well. So this means that we would get an ideal spectrum. We take the average RGB values of each column or each array here, and we end up dividing the two different spectrums against one another to achieve the sample absorbance depicted here.
So one of the things that our MATLAB script needed was some sort of calibration so that we could take these MATLAB values and turn it into a wavelength value. Okay, so the process that we used, we took 3 filters, each running through different wavelengths of light, took an image of it and analyzed the ratio of red to green to blue, then looked at our blank spectrum to find out which MATLAB value corresponded to the same ratio of colors. And that way we were able to get the wavelength values. By doing a linear fit, we were able to then find the equation that could be used to correspond to the rest of the wavelengths that we didn't have filters for. Okay, so now we get into results. This is our preliminary result, meaning these are just a couple of water samples compared to each other. And we did this to analyze what type of noise would be present in our images. And as you can see, there are 3 different areas where we had to worry about noise. So rather than only looking at if there's a peak at a certain wavelength, we had to analyze the amplitude of the peak to find out if there was actually absorbance going on there.
Okay, so now we're going to the results section. So first we tested the red dye, which has an absorbance of 504. This isn't pure red, it's red 40, so that's why it's lower, not in the 700 range. So on the left side is our sample taken with the basic spectrometer. On the right side is with the optibox. As you can see, the point of interest is around 504 nanometers, which we can confirm in both graphs. And then what Amanda was saying initially, this section over here is noise, so we can compare that to our reference. And then next we did yellow. Yellow absorbs at 427 nanometers. That's yellow 5. So on our graph, we're a little bit off, but we account that for initially when you're trying to match the spectrums, that they didn't line up correctly, so that's why they're shifted a little bit. So it's a little bit high, and then again, we can see the noise on the right side.
Here you can see our green sample, which has 2 different absorbance peaks, actually. And we've highlighted them here, but notice that the amplitude is much higher than expected. And we realize that this correlates with the level of noise we've been seeing. So although we haven't subtracted the noise from this, it's clearly depicted that the noise ends up amplifying the actual absorbance value. So we do see a peak there, even though it's not the most accurate, but it's still highly correlating with the original sample absorbance. We also have float, which also has two distinct peaks. Obviously, the one to the left here, between 350 and 450, is much less than the other peak. Although we couldn't really see this peak, we saw a high correlation between the 628 nanometer peak here and here. And the reason why this actually keeps going beyond 620 can correlate once again back to the noise.
Okay, and last but not least is purple, which also has two absorbance areas. Again, we have the right side, which has a lot of noise, but then we also have a distinct peak again at 540 millimeters. Okay, so that was just a proof of concept. So we wanted to relate it to a biological sample. So we chose hemoglobin. The top right picture is just a PBS blank rather than water. And the bottom right is the spectrum at a specified concentration. And if you compare it with the standard hemoglobin absorbance spectrum, you can see a high correlation between the position of the peaks as well as the height.
Okay, lastly, we wanted to test the functionality of our polarizers. So basically what we did is we had one of our polarizers and rotated everyone 90 degrees, so it blocked out the incoming of light. And then we used a plastic cuvette, which is known to change the polarization of light. So as you can see on the left side, we got a black image confirming that there's no light passing through, and then we got the plastic cuvette showing that there's a spectrum coming through. And then for future work, we want to use more filters, which will better improve our calibration curve. We want to make a PMMA casing, so that way we don't work in the dark room. We want to use tissue samples, because that's more biologically relevant. And then we also want to automate our MATLAB algorithm, so it's a little more user-friendly for people who don't understand MATLAB as well. And then also we want to try to find a strong enough portable light source, so that way we don't have to use the generator.
Okay, so we would like to thank Hong from our department for helping us out, our two TAs, Melissa and Shahid, Parks grad student Dollar, and especially
Yes, please hold your applause. We still have demonstrations. Okay. Why don't we move to the table? Group 11, the previous group that went. Do you mind if we borrow your lid? Okay. So now we're about to conduct a test to show that our spectrophotometer really works and we're not just bullcrap. Okay, here it is. Nice, pretty picture. Ryan would just kindly show. All right, it's actually. So as you can see, we have our absorbance spectrum shown right here. So as you can see, we have our absorbance spectrum clearly. All right, so, that's good. So as you can see right here, we have our absorbance spectrum. You can see all the values, although blue is a little weak. And the reason why it looks so weak right here is actually because of all the surrounding light in this room. Normally if this were in a dark room, it would just be extremely intense. And there it goes. So here is our blue stock sample that we've used. And if you can show. There. As you can see, there is indeed a change in intensity. And if you notice, blue absorbs much later to the spectrum, so it can block out a lot of red. Although it's a little hard to see here, we have shown that there is absorbance because there's a lack of red. And now we'll test it with the purple sample. And it's Alright, but as you can see, even though we've actually lost some of our sample, the blue sample clearly showed absorbance in the end. And that is our product.
It works a lot better in darkness.
Yeah.
One quick question and then move to the next one.
What do you mean by the nighttime setting on the phone?
Oh, the settings can pick up different, either more of a certain color or different ranges of colors, or it's all just settings on the phone. There's daytime, nighttime, etc. Nighttime just basically increases, it helps to increase the ISO setting, which basically means the camera's going to pick up more light. Because when it's dark, you need to pick more out.
Well, it's a certain setting on the phone that we were using.